So what about those questions?
Which one?
So that you gave us in the last class, equations.
Yes. Have all of you done that?
So we tried to, but facing issues.
Was there some issue
Yes, sir.
with everybody?
Yes, sir.
Anybody who has done them?
Sir, in question number 2, you asked for a moment of inertia of the hollow section. We had a rectangle with a hole in it, and then you asked to calculate the moment of inertia of the hollow circle. But isn't it same it's similar to the moment of inertia of the circle? Then why we are putting it inside a rectangle? I think there should we be they're asked to calculate the moment of inertia of the remaining section, that is the rectangle with the hollow circle. The question was not clear.
Okay, let me check it first. Okay, we'll discuss it towards the end of the class. I need to check
Yes,
the
sir.
question.
And
Anything
in
else?
question 3, yes, sir, I have a doubt in question number 3. We had a plate.
I don't. Just give me a moment first. I don't remember. I don't remember which was question number 1 and which was third. And let me first check
Third,
it.
third question, we had a hollow plate inside a circular plate, a disc inside another disc.
Just give me a minute. What was it? Which question were you talking about?
A
Now you
rectangular,
can tell me.
yes, a rectangular plate with a hole in it.
Okay, just a minute. Okay, yes. हाँ बताओ क्या इसमें इशू है?
So issue है question क्या है? हमें moment of inertia किसका निकालना है?
You have to find out moment of inertia of hollow section.
Hollow section तो circle है ना?
हाँ, hollow section circle है. About an axis passing through its center of gravity. Okay, it is a hollow
तो
section.
इसका अप्रोच क्या होगा अगर रफली मतलब
No,
आप बोलेंगे?
it's right. It's actually
Sir, it's
I guess remaining. Yeah,
portion.
right. It is the remaining portion. Once you have removed this circular portion, the rest of the section, you have to calculate the moment of inertia or this of rest of the section.
Yes, sir.
तो फिर इसमें
So
सब्ट्रैक्ट
then it
करना है मोमेंट ऑफ इनर्शिया?
हाँ
इसमें फिर
so
सब्ट्रैक्ट
फिर
करना
इसमें
है मोमेंट ऑफ इनर्शिया?
हाँ
ओके, तो वही प्रोसीजर है इसका.
And what was the next question?
प्लेट वाला.
hollow inside a disc.
Hollow inside a disc.
The plate आपने क्वेश्चन में लिखा तो
Plate.
क्वेश्चन नंबर 3.
The mass moment of inertia.
Mass moment of inertia पे.
Question.
Mass moment of inertia. That. Please, can you repeat this problem?
The question is find the mass moment of inertia of a disk
Of a disk.
and density
Okay.
is given.
Just density, how much is density?
8,000 kilogram per meter cube.
Okay. Tell me, what is the issue? Thickness is 10 mm, and we have to determine the mass movement
Mass
of inertia about an axis perpendicular to the page and passing
So
through
perpendicular
pin at O.
point at
Point
okay, sir.
at point O, that is on the outer circle of somewhere at the bottom.
Yes, sir, perpendicular to the tangent, right?
Yes, right.
Okay.
And it has a thickness of 0.01 meter, right? That is 10 mm. Yes, 0.01 mm.
सर आपके पास
0.01.
इसका ये है आंसर
What is it? What is your answer?
0.25
No, that's 0.25. 0.25 किसका है? I guess वो डिस्क का होगा 0.25 और
हाँ सर
7.
क्योंकि वो क्लियर नहीं हुआ था ना क्वेश्चन
That's correct. But you have to find ultimately a moment of inertia of the plate about that pin. IO.
Sir,
IO. Remember.
सर उसके लिए
sir, it
हमने
would
नहीं
be
पढ़ी
सर हाँ आपने नहीं पढ़ाया था लेकिन इसके लिए शायद 5/f² आता है
क्या क्या
वो नहीं पढ़ी थी वो फॉर्म
tangent के perpendicular निकालने की with respect to tangent. So इसके लिए different formulas है.
No, you don't have to use. Why will you use different formulas?
सर आप प्लीज एक क्वेश्चन एक
Then
बार
what is the
दिखाइए
approach? एक बार फिर आप दिखाइए क्योंकि
Okay,
ऐसा
चलो
क्वेश्चन नहीं
ठीक.
किया.
Okay, fine. मैं ये प्रॉब्लम आपको दिखाऊंगा. Today or we will start with next chapter today.
सर पहले यही खत्म करते हैं तो चैप्टर पूरी तरीके से वाइंड अप हो
Okay, चलो
जाएगा
ठीक है. Okay, firstly, what we have, this is our ring, right? And this is the internal one. And here what we have a thickness of 10 mm, right? We have to determine the mass moment of inertia about an axis which is perpendicular to the page and passing through the pin. That is, where is that pin? Here is the point O, perpendicular to the page, which is absolutely tangent to the circle and which is passing through the point at O. Okay, and now we have two dias, one dia here and another dia, let's say, is here. The internal circle dia, which is This one is 0.125, and when it has a thickness of 10 that means it is this external will be 0.125 plus this is in meters. We can also write this in meters, 0.01 meter, and this external will be 0.125 plus zero point 0.1 uh, 0.25 meters. Right. Now, this will be actually, we can do it in this way. We can first calculate the moment of inertia of the whole circle and then subtract the internal one. The external is, this is your external, right? And let's say this is our G point and its radius is 0.25. Okay, minus the internal one. That internal is 0.125 meter. Okay, uh, we can do it this way. We have internal circle and we have an external circle. Now that this has a this plate has a density of 8,000 kg per meter cube, and we say it has two composite parts, right? Internal circle and an external circle. The external one is 200 radius disc, right? This is our 250 radius disc, 250 radius disc, and this is our 125 R disc. Now, the moment of inertia here can be about O. I'm talking about O. Can be actually determined by finding the moment of inertia of each of these parts about O. Right? How we can here calculate the moment of inertia about O is that we will find out the moment of inertia of each of these parts. That is part A and part B. Let's say this is our part A, this is our part B. That can be found by determining the moment of inertia of each part about O, and then we can add them up, right? And then we can easily use here what as we were using parallel axis theorem, right? But in collaboration with the mass moment of inertia, because actually we are dealing with the mass moment of inertia here. So here for a circular disk, your Ig is half of mr square. When we talk about mass moment of inertia, about G is at center. This is point G. This is your G. Mass moment of inertia about G. Okay. Now here, firstly, we have a disk, right? And we have a internal hole in it. Now, firstly, we will try to find out what happens with disk. What happens with disk? About we want to find out moment of inertia, MI, about and about an axis which is actually what? Which is perpendicular to the plane of this disk, and which is again passing through G. Where is G? This is your point, central point G, and that comes out to be, as I have already mentioned, at point G, moment of inertia will be half of mr square. Now here, the mass center of both disks from point O will be same, will be actually 0.25, right? Because from this point to this point, total radius is 0.25. That is true for both the disks. One is the internal external hole. This is your internal hole and your external hole. Your G will be same at the center of the external hole. Now, when you have to calculate mass, that will be, as you already know, it is what? It is density times volume of disk. We are talking here about disk. And that is actually equal, what is the value of your density? That is 8,000 multiplied by what will be your volume. Volume of what? Volume of this disk, right? If you remember, volume of disk will be simply equal to pi r square h, pi r square h, and the value will be 8,000 multiplied by pi. How much is your r? R is 0.25 square multiplied by the thickness of the disk. How much is that? 0.01. Okay, your disk is having a thickness of 10 mm. It is thickness, mind it, it is thickness. I am not talking about this value. This value is a different value. The disk has a thickness of 10 mm. And here we can calculate the volume, we can calculate the mass of disk D. That will be equal to 15.71 kg. This is what? Mass of the disk, right? Now we have to calculate the moment of inertia. Finally, this is what we have calculated mass. Now we have to calculate the moment of inertia about O of what? Of that disk, of the disk, moment of inertia. That will be simply equal to half of mass into r square, which we have already calculated, plus mass into d square. This is your moment of inertia of a mass. It is a simple one as we used to calculate, which was Ig plus, we used to calculate Ig plus AH square. But here, when we are talking about a circle and we are talking about mass, this gets changed into mass parameters. Okay. Therefore, you have already calculated half of mr square, which is 15.71. This was mass of D, right? This is here MD. Half of 15.71 into R. How much is your R? 0.25 square. Okay. Plus mass again 15.71 into 0.25. This is your moment of inertia about O, which is perpendicular to the disk of the plane, a plane of the disk. This comes out to be, yes.
So this is not analogous to area wala. तो यहाँ पे जो d square है ना, what is that? D, is it diameter or radius or what is it?
No,
Distance
this is R.
between
This is R actually. This is R.
है ना, हाँ, that's
This is R. Okay, mr square. Like the way we used to calculate AH square when we talked about area. Here it is R. We are talking about R because the parameters range from O, point O to G. Point O to G. Point O to G is R. Okay, calculating, giving all the calculations. Tell me how much is the value? Please do it quickly. There is actually a reason why I had earlier mentioned it D, because it was actually the distance. It will vary in both the cases. If here it is R, the value of R is again 0.25, and the value of D, the value of D here, which I had earlier mentioned, I had mentioned a D, but the value of D again is same as that of R. In this case, D is actually the distance. Which distance is it? R is your simple radius R, whatever that value is that, and D is actually the distance from where you are actually calculating the moment of inertia. That is at point O. And at point O, the distance from point O to G is again 0.25. It is 0.25. That is why I had mentioned it D here. In another case, when we will be talking about this hole, there again your D will be different. It won't be same as that of R, right? For your internal hole, your R will be different. R is how much? 0.125. And your D, because you are calculating it from point O, that will be 0.25. They are both different. That is why I had used the term D here. Okay, how much is the value of moment of inertia of disk about O?
1.47.
1.47. Okay, what will be its units? We are talking
Uh,
about kg, and we
kg
have
square.
meter. Yes, we have meter square. This is our moment of inertia of disk. Now we will have to deal with moment of inertia of the whole internal ring. Okay, now we have this whole, for which we have to calculate what? Mass moment of inertia about point O. Hole. Simply again, hole is also a circular in shape. Here again, when you have to calculate its mass, that will be again equal to density times volume, right? And density is already given. How much is that? It is 8,000 multiplied by again pi r. How much is r for hole? It is 0.125 square multiplied by height, a thickness. That is 0.01. Okay, that comes out to be 8,000, and it comes out to be. Give the values quickly. 8,000 multiplied by. Okay, that comes out to be 3.93 kg. This is the mass of hole. Now again, moment of inertia about O of what? Of this hole. Now we are talking about hole. That will be again half of m mr square plus m into d square. Why d? Because this d is actually that distance from which you are calculating your moment of inertia, which is at point O, from O. That will be equal to half of How much is mass? 3.93 multiplied by r of radius is 0.125 square plus mass. How much is mass? Again, it is 3.93. Now your d is here 0.25. See the difference. In 0.125 r, here it is 0.25 square. In previous case, when we were calculating the moment of inertia of the external disk, their R and H were different. They were same, but here we have a difference. The reason being the point from where you are actually calculating the moment of inertia. So your I0 comes out to be, have anybody calculated? It comes out to be 0.276 kg meter square. Okay, now you have calculated moment of inertia of both disk as well as. Now you have to calculate the moment of inertia of plate about the pin. About the pin. Therefore, you can simply say that will be equal to moment of inertia of plate about the pin. That will be simply equal to I0 will be equal to I0 of disk minus I0 of hole. That will be equal to 1.473 minus 0.276. That will be equal to 1.20 kg meter square. This is the value of your I0. This was your problem. Is that clear now? Is it clear now, Zarka?
Yes, sir.
Okay. Shall we move? This was your homework, but unfortunately, ये भी आपने मिस ही करना है. Okay. Anyways, shall we move ahead now? Sahil, shall we move ahead?
So,
Okay, when you see this word structure analysis, what is it that strikes your mind? Like, what is structure analysis? Does anybody have any idea? What is it that strikes your mind when you see the word structural analysis? Anybody? None of you have any idea about this? Zarka, you tell me.
So structural analysis could be like we check how putting a load on a structure or something would affect the structure, basically, as the word says.
You are about to start the journey of being a civil engineer. You should be at least having a good idea about structural analysis. Sahil, can you tell me what is that which strikes your mind when you talk about structure analysis? Yes, Sahil. Sahil, are you able to hear me?
हेलो.
हाँ बताओ.
हाँ जी सर. सर
What
मेरा
is structure
डिस्कनेक्ट हो जाता है
analysis?
बार बार.
Okay. What is structure analysis?
सर स्ट्रक्चर्स को देखना या एनालाइज करना स्ट्रक्चर्स को. समथिंग अबाउट दैट.
Absolute layman definition.
Sir, that I have no idea. We haven't encountered any such thing
No,
so far.
apart from, I know you might not have been dealing with structural analysis, but being in this profession, I mean, you should be knowing what it actually means. What is it all about?
So to analyze the structures.
Okay, fine. To analyze. Uh, Analyze means what? Can anybody else add something what Sahil has said? Actually, structure analysis is whenever you have any structure, it has been loaded. Now, load can be of any category. It can be it can be a dead load. It can be a live load. It can be a seismic load. It can be a wind load. There are a number of loads which can come upon these structures. Just give me a minute. Hello. Okay, so whenever we have any sort of structure and it has been loaded, what we need to understand is its response. Now, how will it respond? Towards those encountered loads. And studying that response is actually structure analysis. What kind of deflections can the structure be incorporated with? Will it be strong enough to tackle those forces, or it can fail? Or you need to understand what are the movements, what are the forces that it can withheld within the framework of its structure. Similarly, you can give number of examples of structures. Now, it is not only the man-made structures which we can analyze. We can even analyze our self, human skeleton. Human skeleton, again, it's a structure. And it has joints. It can take loads. It has its own dead load. It can take more loads upon it. And the assemblage of these of the human skeletal is making us to move, to do 100 number of things, to do whatever we want. Similarly, and ultimately, what we are doing, we are transmitting our whatever load that's getting on us because of the skeleton weight, because of the flesh, skin. Similarly, we have these structures. It has partition walls. It has number of structures which are designed as RCC frame structures. They again they have columns, they have beams, they have lintel beams, they have foundation, they have doors, windows, plastering, number of things. they have dead load, and then comes upon the live load. Live load is like we are living in a house, or we have a public building and people come there, add up the load, and that load has to be transmitted. Or like bridge, we have to design the bridge to sustain them or to take their own load as well as the load of the traffic. And then we have to understand, we have to get into this, that how will this structure respond now to load? Will it get deflected? Will it have a plastic deflection in the range of plastic zone, or it will deflect in elastic zone only? Or there can be cracks, there can be deformations, there can be number of things which can lead to the failure of any structure, which we have to take into consideration, and we have to understand where we can actually stop the structure to get to fail. Okay, and all these necessary steps should be taken by definitely a structural engineer. We are least bothered about the aesthetics. We need what it should be structurally sound. The response should be sound. We have to design in such a way so that it responds to the loads that can come upon it. And for that, we need to analyze. Firstly, analyze it. Analyze what? Analyze what will be the movements which can get developed on the structure. What will be its shear forces? Primarily, we talk about shear force and bending moment. And in some case, in some structures, we have to deal with torsion as well. And all these things have to be taken into consideration while you are analyzing. And finally, once you have analyzed what amount of load can come on a structure, and what amount of movements or what amount of shear force can get incorporated in these members, right? And you give the value of those movements as well as your torsion movements, your shear force, and you will have to see. Ultimately, once you have given, you have taken the response of the structure. Now you have to deal with designing process. And in designing process, you will have to deal now. You will have to design the structure in such a way so that it will take care of those calculations which you have done while analyzing the structure. And accordingly, it has to now design the structure. It has to design the concrete mix. Now we have to design the arrangement, or we have to see what amount of reinforcement do we need, and what amount of sectioning do we need. And all these things cater the only once you have analyzed the structure. And analyzing does not only mean that you have to calculate shear force and bending moment diagram. You of times have to see that whether the structure is stable or it's unstable, and what are the parameters we need to see before designing any structure. That there we have number of parameters. We have to see the zone in which, like for example, we belong to zone 5 of seismic radar. It's highly seismic prone area. And for such regions, what are the necessary steps that we should take in order to construct our buildings in region zone 5? Then we have environmental conditions as well, right? We have to take care of loads which will come because of the environmental constraints. Like we have to take care of the snow load, which maybe many of the regions in, let's talk about India, don't have to take care of. But here in our region, we have to take care of number of things. Like I said, being a highly seismic prone area, we need to see what amount of cyclic loads can come due to lateral loads, which is seismic loads, or even with wind loads. Uh, Usually, we don't here in our region we don't have that amount of high winds. So, what we need to cater here is or take care of the our seismic loads, which we hardly take care. And in our region, it's never feasible or advisable by any of the structural engineer that he or anybody can go for simple masonry structures. But usually we construct simple masonry structures as our residential houses. But nowadays, arch frame structures are coming up mostly when we are constructing commercial buildings, public buildings, and so on. And these are the best suitable at this point of time. But nowadays, new technologies are also coming up, like confined masonry and so on and so forth. You need not to go into that as of now. So here, what you need to understand is you need to now that you being civil engineers, what you should always do, what I suggest you to always do while you are roaming, you are at your home. Try to have a look at all your construction activities going on in and around your house or wherever you go. Try to see what is the reinforcement that the construction people are using, how the RC frame structures are constructed. What is it that's making them more efficient for seismic? So, structure analysis is one of the most important subject in your civil engineering. We will be having right now. We don't have much of the content in just one chapter. From your next semester, you will get to know about structure analysis. We have structure analysis one, we have structure analysis two, we have advanced structure analysis, and so on and so forth. So there we will be studying in detail what is the structure analysis all about. Here you will have to just get an idea how the loads are actually coming on structure and how the structure itself behaves against that load. That is how will what will be the forces that will get or unknown forces that can get developed in the structures. And again, here what I was telling you was that you should get an approach towards understanding these civil engineering things now. You should see how slab is casted, how reinforcement is being incorporated in any of the structure. You should have that analytical skill to get. You should boost it in such a way so that your analytical skills get developed. Although this structure analysis is actually a mathematical algorithm which we have to deal with. But apart from that mathematical algorithm, it is the better understanding of structures also, which is very important, which cannot be studied from books. It is actually how you understand the structure on the site, how you actually see this structure, how you see the loads coming and unknown forces getting developed inside the force, and how the loads are getting transmitted. That is a different thing, and it's a really important thing which you should understand and try to get over these skills to understand better any structure which is in front of us anywhere. Yeah. Anyways, what we will be dealing here is absolutely basic things. I guess you will be having some idea regarding these. That is, we need to understanding the loading actually first. How loading comes on a structure and how material resists those loadings. Right? It is actually the material is resisting, and the sectional properties. and the designing, which we have to deal with. Here we will be firstly seeing if we have a structure and some load come on it. So let's make you understand with an example. Let's say we have a cantilever, right? And let's say it had been loaded here. It has a load here, and it has one more load here. It is fixed at point A, and it has a load at point B, and it has again a load at point C. Now what we need to understand here, how we can actually understand what are the internal loadings. These two are what they are, external loadings, right? A point load has been put at point B and at point C. Now we will have to understand how internal unknown forces gets incorporated, and usually that we do that by the method of sectioning. By the method of sectioning, we do that by using method of sectioning. And now what does this method of sectioning mean? Like I will make you understand on this diagram, which is a simple cantilever, and it must be having some cross section, right? And here what we will do, let's say I have to see what actually happens internally at point B, right? So in order to at point D, sorry, it is point D, at point D. So at point D, what I need to do, I will say I have a section at that point. It is an imaginary section, right? It's an imaginary section to understand properly what actually happens at point D. So here what we have placed, let's say this is A dash, we have placed an imaginary line at the same point where we want to understand what is the internal loading. And then we try to separate these two segments. Now we have, this is fixed, we have this segment, and then we have another segment, right? And we have two loadings here. Okay, this is your point D, this is B, this is C. Now at any point, let's say here we have considered A section at point D. We now that we have separated them, the internal loadings at B will now be in such a way so that it will become external actually. Now if I have sectioned it, because of these two loads, A load and B load, there was some internal loadings, right? There were some, I don't know what was it, there was some loading here, there were loadings on through actually throughout the beam. Now when I have cutted it, so cutting means what, I will make those internal loads now as external loads on any free body diagram. Those will be now, it will be having a reactional force here, it will be having a reactional force here, right? And it will be having a normal force here, it will be having a normal force here, right? And it will also have a couple moment. It will also have a couple moment, which will be like this here and here. Okay, these will be now couple moments actually. These are at a point where I had made a section, I had cutted it out, and I had drawn an imaginary line to understand what will be these are now external loadings. The moment I had made a cut, now these loadings which were actually internally inside the beam, Now they are external. They are now external loadings. As we have already for any coplanar section, in order to understand the equilibrium of equations, we have summation of forces into x0. That means we have forces in direction x, we have forces in y, and we have movement in
Excuse
z
me, sir.
direction. Hanji.
Sir, ये
Yes,
external
Sahil.
loading समझ में नहीं आया.
It is not actually. What are these? These are, once I had made a cut. What has released? There were actually internal forces. Those internal forces were what? All three of them. They were normal force, they were vertical one, the force in z direction, and a movement in z direction. आपने कोई चीज कट कर दी, that means all those have released now. Summation of forces in y has released, summation of forces in x have released, and summation of summation of movement in z has released now. Now you have to calculate these values. You have to calculate these values. Actually, this is all imaginary. This is imaginary. This is not actual. You are imagining it. You are imagining that at every point on the beam, there will be one normal force, there will be some force in x direction, there will be some force in y direction, and there will be a movement. When we are talking about coplanar structures, here we have a coplanar structure. We don't have 3D structure. In 3D, we have a different equation of equilibriums. Equation of equilibrium. Here, we have an imaginary idea that at every point on the beam, there will be three unknown forces internally, right? What will be that? There will be some force in x direction, some in y, and movement in z. Now, what are those forces? Now we can name them. Now we have actually two sections, right? I had made a cut at point A. This is your point A. And this is your point B. And this is a free body diagram now. I have released what it has given at its fixed ends. Now this is a free body diagram, right? Free body diagram. Now I had said, now that it has two loads, right? It will be having force in x direction, okay? It will be having another force in y direction. It will be having y direction, and it will be having a movement. It will have a movement. Let's say this point is, this is your point which D, right? So this movement is actually, this couple movement is movement at D, and this is your shear force, this is VB, and this is your NB, normal force at point B. Now what we say actually here, at every point we have a normal force, we have a shear force, and we have a bending moment, which you have already understood. By making a simple cut, you got an idea that at every point we will be having three unknown forces: normal force, this is our normal force in x direction. For somewhere forces in x direction are called as normal force. They are actually perpendicular to the cross section. They are perpendicular to the cross section, and that is called as normal force. And now VB. VB is what? VB is a shear force. VB is shear force. And it is basically tangent to the cross section. NB is, it basically acts perpendicular to cross section. NB is normal force. And our VB is actually shear force. And it is tangent to cross section. It is tangent to cross section. And then moment. We have MB, which is a couple movement, which we refer to as bending moment. Referred as bending moment. Again, we have one more thing which Newton has said in his whenever we have any loading, there is an equal and opposite load on the other direction of the segment to understand the equilibrium. Therefore, we can say if on the left side of D we have normal force MB, we should be having another normal force in the opposite direction, that is NB again. If we have VB on the left hand of this beam, we will be having another VB which is an opposite in its direction. We'll be having another movement at point D in opposite direction. This is your clockwise direction. Here we had anti-clockwise direction. So at every point, whenever you make a cut, you will be having two sides, one on the left and one on the right. And both of them will be having equal movements, but in opposite direction, equal shear force, opposite direction, and equal normal force, opposite in direction. And at every fixed point, we have a fixed connection here. For fixed connection will give you again, if it will give you normal shear force, but here it will be in opposite to the direction of what is at point B. It will be in opposite direction, right? And then you will be having a normal force and you will be having a moment. You will be having a moment also for fixed beams. We will discuss that in when we will study different types of support reaction that you have to deal with. Now, here again, as I added, we should have to also satisfy the condition of equilibrium. Summation forces in x should be 0, summation of forces into y should be 0, and summation of movement in z direction should also be 0. So this basically have to be taken here again into consideration, the stress distribution. For example, now that this beam has been loaded, here with 2-point loads. One is at point A and one is at point B. Now we have to understand also how will the stress in these beams get distributed? What will be the pattern of stress distribution? That is and we need to understand the resultant of stress distribution also. That is actually over the member's cross-sectional area at its cut. We have not gone into that. That will be against the cross-sectional. That stress distribution will be against the cross-sectional parameters. Now that you had already came into this notion that whenever we have to understand the internal loading pattern or the stress distribution, you have to imagine something. You have to imagine what will be the loads that are actually going to come on these structures at every point. This was with regard to what? This was with regard to simple coplanar sections, right? Where you have normal force, you have NB, you have a movement, you have a movement, you have shear force, you have movement, you have normal force. Normal force and B will be simply calculated when you take summation of forces into x0. And your shear force VB will be summation of forces into y. And your moment, bending moment. B moment MB will be calculated summation of moment in at B0. These are the conditions to calculate our three actual unknown loadings whenever we talk about normal force, shear force, and bending. Now, before we can go further, we need to understand. I guess you will be having an idea regarding the sign conventions that we take here. For we are dealing with three types of unknown forces. Firstly, normal force, shear force, and bending moment. We should be able to make a sign convention before going or before analyzing any structure. And what does that sign convention mean? Sign convention means you will be having some positive values and some negative values, right? It's about positive and negative, getting the values of exact conventions. Although I would say this choice is arbitrary. Anybody can choose clockwise movement as positive and anti-clockwise as negative, and some other can choose negative. But whenever you are dealing with the problems, the sign convention should be from the start of the analysis towards the end of the analysis. Actually, you should plan one convention at this point of time and solve your problems as per that sign convention. Don't change your sign conventions on and off. Otherwise, you will put yourself in trouble. Make a sign convention today and follow that throughout your life. Usually, what is that sign convention? We say whenever we have a cut on any beam, let's say we have this beam and we have made a cut at point at the center of this beam. Okay, this is the cut at where we have made. So what we say usually here is we have two parts. One is our left part and another is our right part. There will be two different sign conventions for the left and for the right, right? So here whenever we are making any cut, as I have already told you, uh, there will be three forces on each side of the cut. Firstly, you will be having a shear force V, you will be having an opposite shear force V, you will be having a normal force N, and there will be an opposite normal force N. Okay, and then you will be having a movement, one on the clockwise direction and another on the anti-clockwise direction, M. Now you have to choose a sign convention. How will you choose that? You will say whenever, as you already know, they all, if you have six unknowns here, There are actually only three unknowns, and the rest three are opposite in direction. Simple. If we have three unknowns on the left side, there will be equal in magnitude on the all three of the unknowns will be equal in magnitude on the right side, but they will be in opposite direction. Now, here firstly we have to deal with what we have: force, normal force. These are two sections, same. We will be having two normal forces, or we will I'll make you understand this way. I have a simple section of a beam, and whenever they are pulling apart, here it is tensile forces are getting generated. Here you will be having tensile forces because we are pulling them apart. In that case, you will be having a positive normal force. And when it is in compression, when the forces are such that the member is getting compressed, then in that case you will be having a negative normal force when it is in compression. This is a okay, fine. Now whenever we have this what we call as shear force, such that it is moving in a clockwise direction. Here if you will see, this part of the element is actually on right hand side, it is going down, and on the left hand side it is coming up. That means it will be moving like this. So this is a clockwise direction. Assume this shear force as positive. Okay, and whenever you have a movement such that it is clockwise on the left end, and certainly it will be anti-clockwise on another end, right end, and making it concave or bend downwards then your movement will be positive. And if it is such that the movement is this way, then it will be negative. This case positive, this case negative. Now this was your sign convention, wherein you have said that whenever we make a cut on any member, the normal force when it is a tensile forces, or when you are pulling apart two sides of the same member, then the normal force will be positive, and if vice versa, then it will be negative. And in the shear force, if it is internal shear force, v acts downwards like this. Here it is downwards on this direction, and the movement at that very direction is a counterclockwise direction at point B. So here you will say this normal force is trying to elongate the member. Positive shear force tends to rotate. This is shear force. This is moment. And this is your normal force. Here you can say positive shear force. When we talking about positive shear force, it tends to rotate the segment clockwise. Positive shear force tends to rotate the segment clockwise. Okay, and positive bends to bend segment concave upwards, right? This is your concave upwards. positive bending moment tends to bend the segment concave upwards. Okay. This was the sign convention which you will be dealing now with. You can add thing in order to understand it more. Now that when we were talking about the uh, this is this normal forces, this segment, when we make a cut of it, for example, this is a cut now, this is a cut. Therefore, now the direction will be this points, normal force, when we make a cut, right? This is how it will be at the cut point, and it will be elongating it. So therefore, you can say this is a positive normal force. And when we talk about shear force, when we have a normal force like this, positive normal force, it is moving clockwise. And if we had made a cut, then internally it will be in the opposite direction, right? This will be this way and this will be this way, upward and downward. It will be downwards towards the left and it will be upwards towards the right. And whenever we have a concave movement, which is now positive, if we will make a cut, internally the direction of the positive movement will be like this. Okay, these are the sign convention which we have to deal with. And there, whenever one more thing, whenever we talk about calculating shear force, bending moment, and normal forces, usually we have very less magnitude of normal forces. We have maximum forces, or the design or the analysis of the structure analysis primarily depends upon one, that is shear force and bending moment. It primarily depends upon shear force and bending moment. The values of normal forces are quite negligible. We almost all the times neglect calculating normal forces because they hardly get into providing the strength to the section. These are the two primary things which are dependent or which are responsible in order to analyze the structure for given loadings. Or whenever whenever we talk about three-dimensional or space trusses or space elements or three-dimensional elements, there we need to calculate what, as you already know, there is a component, there are bending moments, there is a torsional moment as well. We need to calculate that torsional moment also. So here we don't have to deal with those three-dimensional structures. We usually deal with coplanar structures for which we have to calculate the shear force and bending moment diagram. And now here shearing means what? If you have this element, if there is some load at this point, there will be some force immediately after that point. And this is shearing force. This is the force that goes in one direction on the one side of the segment, and another comes on the another side of the segment. And bending movements, as you already might be knowing, bending movements, they are actually couple movements. They tend to these forces tend to rotate the body, which are being resisted by providing the resisting moment, and we need to calculate that resisting moment capacities of any segment. I think this is enough for today. We'll